Hello. So, in our last lecture we discussed about different interpolation families, Lagrange, starting with Lagrange interpolation, simple polynomial interpolation based on function values at nodes of interpolation, and then alternate form of polynomial interpolation, and that is in the Newton form, and then also we followed it, we discussed the efficient way, the optimal way of computing polynomial, that is Horner's algorithm, that is based on uh, minimizing the floating point operations while evaluating the polynomial at any value, at any value of the independent variable. Then we discussed what if the importance of sampling points, that is if we are not careful in choosing sampling points or nodes of interpolation, then even if the function values are the interpolation function may exactly agree with the specified function values at the nodes, but in between nodes there can be very wild fluctuations. And with suitable Chebyshev roots of Chebyshev polynomials, we saw that they provide a suitable or a very nearly optimal location of nodes, and the error or the oscillation between the nodes of interpolating polynomial is very much under control, and we can consider constructing a very good quality of approximation by using roots of Chebyshev polynomials as the nodes of interpolation. Then another way to constrain the errors or constrain the behavior of interpolating polynomial is by adding more information during interpolation, and that is by considering not only function values, but also the derivative function, the constraints, imposing constraints on the derivative of the function at the nodes, and that leads to what we call as Hermite polynomial interpolation. And with just two nodes we can actually pass a cubic polynomial, cubic interpolation polynomial based on two conditions at each node. So, total 4 conditions are available for evaluating unknown coefficients. So, a cubic polynomial can be interpolated, and that is what we call as a piecewise cubic Hermite interpolation polynomial. And this is a very useful tool, piecewise cubic Hermite interpolating polynomial, p-chip, that is used for interpolating data between 2 points, and with the guarantee that the trend, whatever may be the trend of data, is it ascending or descending, that trend it will be preserved. So, we are not disturbing the trend of data when we interpolate using p-chip. Now, another kind of interpolation that is often used is spline interpolations, and as we saw in the during the approximation of Runge's polynomial, Runge function by polynomial interpolation, the primary source of problem was that we were trying to interpolate, we were trying to develop the approximation over the complete range at one go. So, global approximation, the kind of global approximation that we were trying to control, that we were trying to develop, and obviously that is a very ambitious goal, and we are not in control of all the points in the domain of the range at the with the same degree of control, and it might be better to divide the range and then construct approximation over smaller ranges. So, that is what we call as divide and conquer with smooth operation. So, that p-chip that we discussed, cubic Hermite interpolation, just 2 nodes at a time, and that will allow us to fit a cubic interpolating polynomial. That was also that can also be considered as part of this strategy, divide and conquer. But cubic spline interpolation, splines, they have higher degree of smoothness than p-chip interpolation. In p-chip we only considered the first degree of derivative, first order derivatives to be included in the interpolation information. In spline, we use higher order derivatives also. So, the function that we generate is approximation that we generate is much smoother than the p-chip interpolation. So, as we were saying that this is based on the primary source of errors in approximation is the attempt to construct a single approximation over the whole range of the variables. If we can divide the data range into split into smaller parts and construct approximation over individual parts, we can actually get a much better approximation, and that also needs to adhere to the continuity between adjacent data ranges. So, when we divide the entire domain into separate ranges, smaller ranges, then we also need to take care how the variation happens or how the information exchange happens between the boundaries across these smaller ranges. So, continuity has to be ensured to make sure that the function looks continuous and there is no jump in the approximation across the boundaries. So, as I said, p-chip approximation is one such approach which preserves the trend of data, and spline, cubic spline, we can actually generate higher degree of smoothness than p-chip, but at the cost of losing control over the trend. So, while the function that we the approximation that we can develop using cube splines would be much smoother, much more pleasing to visual as appeal, have much higher visual appeal than p-chip, but there is no guarantee that trend of the data will be preserved. So, theoretically a spline is a function that consists of polynomial pieces joined together with a certain smoothness conditions. Now, that so the points at which the function changes its character are termed knots in the theory of splines. So, instead of nodes, we call those points between which we are defining one particular segment is called, they are called the pair of knots. So, for n plus 1 knots, there are n number of polynomial segments. So, between 2 points we will have one polynomial. So, if there are n plus 1 knots, then there are going to be n number of segments, and these are what we call as spline segments. So, denoting them by S I as a function of x, I ranging from 1 to n. So, these are n number of spline segments for which we need to satisfy the continuity conditions on the interior knots. So, on the interior, I mean there are n plus 1 knots. So, 2 extreme knots denoting the boundaries. So, there are n minus 1 number of knots which have to satisfy the continuity conditions. So, cubic splines, we can have splines of various degrees, but cubic splines are most often used, they are the most popular spline functions that are used. So, cubic splines which satisfy continuity requirements for up to second degree derivative are aesthetically very pleasing. So, that explains why cubic splines are most popular spline functions that are used in function approximation or even graphs. I mean, if we just rely on some plotting softwares and leave it give the data and leave it at the mercy of the software to plot a best fit curve, then the chances are it will be a spline fit, cubic spline fit. Splines of degree higher than 3, in addition to having more computation, we do not generally find any significant advantage in the as far as the interpolation or information regeneration goal is concerned. So, for cubic splines, we impose 3 continuity conditions on the spline segments. So, the function value itself, the first derivative and the second derivative, these are imposed at the interior knots and that gives us sufficient constraints and continuity to ensure the smoothness requirement. So, for n number of segments of cubic polynomials, obviously there are n number of cubic polynomials and each cubic polynomial requires 4 conditions, because there are going to be 4 unknown coefficients for a cubic polynomial. So, total number of 4 n conditions are required to uniquely define n segments of cubic polynomials, right. So, where do we get these 4 n conditions? So, let us count our conditions that we have. So, 2 n conditions are provided by the interpolation requirements at the 2 ends of n segments, right. So, the basic I mean there are n number of segments. So, at each segment is defined by 2 ends and both ends will have, there are 2 conditions for each end. So, n number of segments. So, there are 2 n conditions that are available in all. The function agreement, the function value approximation has to agree with the specified function value. Additional 2 constraints are available at each of these interior derivatives, that is interior knots. So, twice n minus 1 conditions are provided by ensuring the continuity of first and second derivatives at the n minus 1 interior knots. So, the first derivative of the function, spline function across the boundary has to agree, the second derivative of the spline function segments have to agree across the boundaries. So, adjacent spline segments, they have to be consistent, not just with respect to the function values, they also have to ensure that the continuity of first and second derivatives are maintained across the knots. So, that provides us how many? So, 4 n minus 2, we are still left with 2 conditions to be provided, and the remaining 2 conditions are made up by assumptions. We assume second derivative to vanish at the first and last knot. So, this is once if we make this assumption, then the leading the spline approximation that we get is referred to as natural cubic spline, or we can specify if we have additional information what is the second derivative at the first and last knot, we can specify those values and that would be specific to the particular case. So, it will still be cubic spline, but it will not be a natural cubic spline. So, determination of appropriate natural cubic spline for a given set of data or knots, it begins with Lagrange interpolation of the second derivative. So, second derivative, we want second derivative to be continuous. So, obviously, then we define Lagrange interpolation that will ensure that continuity is maintained. So, Lagrange interpolation of the second derivative of the spline function is defined, and let us label if we call these second derivatives whatever the values may be as some variable unknown z, then there are n plus 1 number of z. So, that those are the second derivatives with the condition constraint that first and last second derivatives are 0. So, that is the condition for natural cubic spline. For if we do not want, if we have additional information of second derivative about at the starting and end points, then those values can be substituted at these boundary conditions. So, for each segment we can construct the interpolation between second derivative as a Lagrangian interpolation, and this is what I mean, any segment will be bounded by two values of the second derivative, and we can construct piecewise Lagrange interpolation over each segment. So, once we have this second derivative as a linear function, then we can integrate it and derive the spline functions with some unknown coefficients c and d. Those are the unknown coefficients. So, we have this cubic, I mean second derivative is a linear function. So, if we integrate it, then we will get a cubic function, and that is what we arrive at by integrating that Lagrange interpolation. Now, these coefficients C I and d I for each segment, each of these I segments can be derived by imposing the constraints. So, that is just a rearrangement of terms for ease of computation. So, these C I and d I, they are evaluated in terms of derivatives, second derivatives, and then we impose the condition on interpolation condition on this spline approximation at the endpoints of this spline, and that gives us a set of simultaneous equations to solve. And then once we solve the simultaneous equation, that yields a set of values which for z the second derivatives, and once we have computed, once we have the second derivatives available with us, then we can substitute it back in this approximation, and all splines can be derived over each segment. So, you can have a look at this spline interpolation, but the whole idea of this spline interpolation that I wanted to discuss is you can get the derivation, and you can look at the numbers and work out the numbers and plot the spline. The Runge function is a good example to try out spline interpolation and see what difference it makes to the approximation, and it is almost indistinguishable. At least graphically you cannot distinguish between the original function and the cubic spline interpolation, and for that matter even p-chip will do a fairly decent job of approximating Runge function, and that gives us the idea, and I mean that brings out, the entire process brings out the emphasis on the basic philosophy of approximation, function approximation: divide and conquer. So, instead of trying to approximate over the whole range at one go, it is always better to divide the domain into smaller subdomains and then construct approximation over each of these smaller subdomains with certain constraints that will ensure certain degree of continuity across the adjacent subdomains, and as a whole we can develop a very good approximation that will satisfy all the I mean for all practical purposes for engineering analysis. And while we are at the topic of interpolation, we will also try to wrap it up by using by discussing one of the interesting applications of interpolation theory in a very different context. So, we can actually find a very good approximation for function derivative by using interpolation, polynomial interpolation, and that is a many times we need differentiation. For example, if we are using any optimization process, then gradient is a very often requirement. We need to find out gradient of the optimization function, and that is a very often required process, and the convergence of many processes depends on how quickly we can find the gradients, and how accurately or what is the quality of computation, or how accurately we can compute the gradient, because that is what will define the search path for optimal solution, and several other instances where gradient information may be required. So, typically a gradient derivative of any function is often approximated by finite difference approximation. So, by theoretical definition is the limiting operation, and in finite difference we throw out the limiting operation and we just take the finite difference. So, the function values at two different points divided by the difference between those 2 points. Now, as we were discussing about the floating point operation, if the separation between 2 points, the h in this case that you are seeing here, the points that we are sampling the function are separated by some distance h, and we are taking the limiting operation as h tends to 0. So, in practice it has to be a small value, h value is very small, and then we can consider this finite difference approximation to be a good approximation of the derivative. Now, while we were discussing about floating point operation, we also realized we also saw that the difference between two numbers which are nearly equal always leads to a catastrophic cancellation and loss of precision, severe loss of precision, and this is what happens in finite difference approximation for computation of derivatives. So, f of x plus h is not going to be very different from f of x. Function evaluated at x is not going to be very different from function evaluation at x plus h. So, these two numbers are likely to be very close to each other if h is not very large, which should be small. H should be, the difference should be small if we have to approximate the limiting operation by any reasonable degree. So, now we have Devil's alternative. If I use too large value of h just to ensure that function values are different, then I am not probably getting a good idea about the derivative, local derivative, and if I reduce h to a small enough number, then the chances are that we might incur very heavy error in computation of derivative because of catastrophic cancellation and loss of precision. So, what to do? So, this entire process is a first order accurate process, and that is based on the Taylor series approximation, that if you can look at this finite difference and expand function at in the neighborhood of x plus h, then from the Taylor series expansion we can get the error of accuracy and what is the. So, the error term is second order. So, this h square error term is first order, because this h square corresponding to coefficient h square gets divided by h, and that is how it is proportional to linear power first degree of h. So, that is a first order accurate. The error term is proportional to the first power of the separation h, and we can actually work it out by backward difference. One is forward difference and another expression, second expression is using backward difference, no change at all, nothing great. What this allows us is to work out the error, use this to cancel this error term, and if we add these two approximations of finite difference, then we can get the difference between twice the interval, and interestingly the error now becomes second order. So, if I change the finite difference approximation to twice the interval, then the error in the approximation of finite derivative is of second order. So, from the first order accurate I go to second order accuracy. So, I can define a function which is an approximation. So, this particular difference operator, I use this as the basic function, that is approximating the finite the gradient, and then there are error terms. So, quadratic error, and then there is fourth degree error. All odd terms will get cancelled out during the process of these additions. Odd powers of error term, they will get cancelled out. So, since h is an arbitrary interval, I can choose anything. So, if I choose h but to half the interval, then this error term is also going to reduce by h by, I mean replacing h by 2. So, the second term becomes h square by 4, third term becomes h to the power 4 by 16. So, I can eliminate again the h square term, adding the two terms and looking at this approximation. So, I can eliminate the terms from these two expressions and find out what is the error term. So, the function value that I have for as a function of for the sampling of h, and another approximation for the sampling of h by 2, and then the function derivative that I get is now has an accuracy of fourth order. So, considering that we initially we were having first order accuracy finite difference, now we are looking at fourth order accuracy of the finite of the gradient function, and without incurring catastrophic cancellation. So, which is fourth order accurate approximation for the desired function derivative, and this function phi of h, it converges to the desired gradient as h tends to 0. So, however, we can't really compute f of h at h is equal to 0. So, what we can do is we can construct interpolation function as an approximation for phi h, and that can be evaluated for h is equal to 0. So, a sequence of phi h for different intervals can be generated, and an interpolation polynomial in terms of h can be constructed through this data set. And once we have this interpolation polynomial, then we can find the appropriate function derivative at h is equal to 0 as an approximation, and that would be a very good approximation for the function derivative for further use, which will hopefully not suffer from catastrophic cancellation and loss of precision, and the computations would be more stable and more robust. So, that ends our discussion on polynomial interpolation, and that provides the basic background for construction of finite element approximation. I will come back to this basic theme that we discussed today, divide and conquer, that forms the basis of finite element approximation, and we will keep on going back on this theme again and again. Divide the domain into subdomains and construct approximation over subdomains while ensuring continuity across the boundaries of subdomains. Another issue that we need to discuss that will be useful, extensively used in finite element approximation or construction or implementation of finite element method, is numerical integration. Finite element method wouldn't have been successful, wouldn't have been as successful as it is today had it not been for digital computers, and all computations have to be finite element formulation, they have to be cast on a for application on a digital computer, and integration is an integral part of that, and that is what we will discuss in our next lecture, numerical integration. Thank you.